Hi, everybody, from the sunny shores of Wellesley. No, maybe not. It's pouring rain outside. The beauty of a virtual screen and a virtual backdrop is that you have no idea that it's pouring outside. Miserable here at Wellesley. But it's really nice in wherever this virtual ocean and beach is. I hope it's really nice where you are, and I hope you're all doing well and feeling well. And everybody you know is staying safe and healthy. This is our lecture 19C, and it is on section 8.6 through 8.8 in Hornbeck. This is the time where we're going to look at SN1 reactions and finally get to them. We've been talking about SN2 reactions the entire time because they are the favored child in reaction mechanisms. They are very controlled. You can make sure you know you're doing a backside attack and getting an inversion. Where when it comes to SN1 reactions, they're kind of like the bad seed in the reaction mechanism family. They are wild. They are out of control. Hard to predict what you're going to actually make. And so that's why I left them for last. Oh. All right. I thought I'd bring Luna in here to, take a look at you guys as classmates down there. So she is a cutie. She was barking at the mailman a second ago. So maybe you'll hear her do that again. But she loves Orgoland in cyberspace just as much as I do. And so I have to have another animation just for you guys. All right, let's go back and look at this old slide. This was way back in lecture 16, where we first introduced the topic of nucleophilic substitution. And what we did is we looked at these two reactions that were, looked very similar. The only difference was their solvent, and one seemed to have a different rate law than the other. And this one should now look very familiar to you. Oh, let me make sure I got the pen on here. This one should look very familiar to you. It is an SN2 reaction, and that leaves yes, that the one above is going to be called SN1. And these rate laws are the reason why they get their names SN2 and SN1. But what I want you to keep in mind is what makes SN1 so unique is even though there's this great nucleophile here present in the reaction, can't wait to react in an SN2 process, evidently it doesn't because it's not even involved in the rate law. It's not important at all. And that's the other thing about these reactions is SN1 reactions do not care what the nucleophile is. SN2 reactions, this is very important. You need a good nucleophile for SN2. All right, so let's take a look at the mechanism for this reaction, SN1. The key to this reaction mechanism is the very first step of this two-step process is the most important one. Is the rate determining step, is the slowest step possible. And let me show you why. What has to happen on this organic molecule is it basically has to take its leaving group and have it leave. Just fall off. An organic molecule, it just has a bond, break, and fall off. This is an incredibly slow process. And the entire reaction just waits for the leaving group to just fall off. So this is why in our last video, lecture 19B, I wanted to emphasize what makes good leaving groups, because here, evidently, the leaving group has to fall off. Once the leaving group falls off and creates this tert-butyl, otherwise known as T-butyl carbocation, that carbocation will react immediately as a three-bonded carbon, immediately react with whatever lone pair nucleophile you have in there. It does not have to be negatively charged like the one I have in there right now. This acetate, this is a good nucleophile. I could use a poor nucleophile. I could use the protonated form of this acetate, the acetic acid form. It would work still. So then, because this three-bonded carbon is very worried, I'm worried, please give me a fourth bond, so it immediately reacts and creates this final product here. Keep in mind, this second step will happen so fast, it doesn't matter what nucleophile it is in, it has to have just the slow step. Now, one of the curiosities you might be asking yourself right now, maybe, just maybe, is why didn't this go SN2? Why didn't this great nucleophile just react SN2? We're going to take a look at that reason in more detail, but spy what type of carbon, first name, last name, that you would give this carbon, and ask yourself, would that carbon want to go SN2? If it doesn't, then it can't react in this slow step, and therefore the leaving group just has to fall off, and we have to wait for this rate determining step, and therefore this is an SN1 reaction mechanism. I thought I'd bring the British movie back. Hopefully it works on Zoom. We'll see. But I love this guy's accent. Get ready for the echoes. Oh, maybe not. Oh, let me give it one more try. One more try. Yeah, oh, go for it. Oh, bummer. Okay, dang. It worked before I had it on Zoom, and now it doesn't want to work on Zoom. All right, enjoy this little video.
Tertiary halogenoalkanes undergo SN1 reactions, where S indicates a substitution reaction is occurring, N indicates that a nucleophile is involved, and 1 indicates that only one species is involved in the slowest rate-determining step. In tertiary halogenoalkanes, the small hydrogen atoms in primary halogenoalkanes are replaced by bulkier alkyl groups. Tertiary halogenoalkane. The bulky alkyl groups do not allow attacking species to approach the central carbon atom.
Bulky for a nucleophile.
Consider the reaction between 2-methyl-2-bromopropane and a hydroxide ion. It has a two-step enthalpy profile. The first step, the heterolytic fission of the carbon-bromine bond, has a high activation energy, EA1, and therefore determines the rate of the reaction. The first step involves only the halogenoalkane and proceeds via a transition state complex to form a carbocation. The second step has a much lower activation energy, EA2, and hence is considerably faster than the first step. The carbocation reacts with the nucleophilic hydroxide ion via a second transition state to form the product 2-methyl-propan-2-ol. Transition state, carbocation.
Planar, carbocation. When it's only 3 bonds.
EA2.
Flat.
SN1 reactions.
All right, I'm glad that finally worked. I don't know if it's going to crash the rest of the movie. We'll find out. Oh, yay. Okay, so carbocation stabilization is the key. If you're going to have a leaving group fall off, it's great to have a good leaving group. But a 3-bonded carbon with a positive charge, that's very unstable. And so the key to doing an SN1 reaction is making sure there's stability of that carbocation somehow. Somehow you give it a way to get rid of some of that charge. So this is the reactive intermediate, as I was just talking about. It's very uncomfortable, but notice I kept talking about it being planar. This is really important. It is exactly planar, 3 bonds, trigonal planar. And so this unhybridized p orbital is going to be significant in the stereochemistry of how these SN1 reactions take place. And I thought I'd show it to you visually from this point of view, and now you had it from this point, and this point, and that point, all sorts of points of view. Okay? How does it stabilize this positive charge? Well, it could do it by resonance. That's something we've seen in the past, that resonance can stabilize charge. But what if there's no resonance, like in that T-butyl group? Okay? Hyperconjugation then comes to our rescue. Please go back and look at how hyperconjugation was used to justify why allylic and benzylic species in SN2 reactions were favorable due to some kind of partial charge kind of sharing of bonds. So that's the same thing that's going to happen here. You are going to have a initial, let's say we want to name this, we could start out, this has only primary, oops, got to come back to my pen. This is a primary aliphatic. And so it doesn't have very many carbons attached to it. Whereas if I make a secondary carbocation, you can see that once I have more carbons attached, and I'm sorry about this sketchy image, but these CH bonds, these are electron density in here. And this electron density has a way of just sharing. And so what it'll do is it will make this positive charge a little smaller. Okay? And then in this situation, it's going to make it even smaller. We have 3 carbons with all sorts of hydrogens that are in sigma bonds that have electron density that is in the same general space as this empty p orbital. So what we want to do is that is going to shrink that down even smaller. I know that's kind of a blurry picture, so I drew it out here, and I want to make sure we're clear. This is even smaller. This has such, having all these CH bonds donating through space, not resonance, but just through space, makes this tertiary carbocation 3 times as much hyperconjugation as a primary carbocation, and making it 3 times, at least 3 times more stable than the primary carbocation. Oops, this slide got in there by accident. Let me get rid of that one and go straight to this one, because now we should address stereochemistry. Stereochemistry of an SN1 reaction now is important now that we understand a little bit about its stability. Okay? So, the very first thing, again, in the slowest step of a SN1 mechanism is the leaving group falls off. And so when the leaving group falls off, then we have our planar carbocation. Remember, the pH stands for benzene ring. So what name do we give this carbon here? That would be a benzylic, would be its last name because it's attached to a carbon on a benzene ring, and there are 2 carbons attached to it. So it's a secondary benzylic. So it's got hyperconjugation, but this also could do resonance. Resonance 2. Okay? Oops, can you hear me? The mic sometimes falls out of that. Okay, so I could get resonance stabilization of this carbocation, but I could also get hyperconjugation. And so it's really a very stable secondary carbocation. The issue now when you see this, though, in this slide here, I want to emphasize the stereochemistry and the planarity of that intermediate, that carbocation intermediate. And that if you add water as your nucleophile, is that a good nucleophile? Is that strong? Oh, that's not strong. That's the first sign that you might be doing an SN1 reaction, is if you have a very poor nucleophile, meaning it's not charged. But it's got a lone pair. So the water can attack still on this planar intermediate, which is no longer chiral at all, and now attack from either side. Chaos, total chaos. You could get inversion of like an SN2, or you could get what we call retention, meaning it stays the same chirality that it started with because you can get an attack from either side. This will produce two products, and this is also the chaos in SN1. Because SN2 was very clean and made only one product. Every time you write the products for an SN1 reaction, if it's chiral, like this one, you would have to show me both forms, the R and the S. Oh, what a mess. So this would make, the final product would be our alcohols. So this reaction is how to take an alkyl halide using water and doing an SN1 reaction to lose all stereochemistry. And what would happen if we had an equal chance of going in both sides? What kind of mixture would we make? Ooh, I can hear it all the way from wherever you are, far, far away. You're right. It would make a racemic mixture, 50% inversion, 50% retention. This is slide 7. If you want to come back and talk about this one, just refer to lecture 19C, slide 7. I'll know which one you're talking about because this is a little chaotic in here. Chaos with SN1. Let's see what else carbocations can do. We know they can do resonance, so that's a possibility as well. And definitely feel free to talk to me about this in the Zoom meeting if you want me to draw the resonance structures for this possible reaction. Well, what else can they do though? Something new that we haven't seen before in any of our resonance structures is they can do things called rearrangements. The carbocations can actually jump. And it's not the carbocation that's jumping. Let me show you what I mean. And it only happens with SN1. Why can't it happen with SN2? Do you make a carbocation in SN2? Nope. So no carbocation in SN2, no rearrangements in SN2. Again, the reason why SN1 is such a bad seed for the reaction mechanism. Chaos, total chaos. That you have to keep an eye out once you decide it's an SN1 reaction, you have to be on the lookout for this possibility. That this was a totally happy secondary carbocation. No problem. But notice it's sitting right next to a tertiary carbocation. And so I wish the carbocation was on the tertiary. That would be more stable. So what happens is this hydrogen actually jumps and takes its pair of electrons with it. Both the H and the bond move. It's called a 1,2 hydride shift. And this creates a much more stable tertiary carbocation that's in a much happier world. Let me go back. Mic issues. All right, but you get to see a preview of the excitement that's about to come. Tertiaries, okay, carbocations are much more stable than secondary carbocations due to hyperconjugation, okay? Keep in mind, we'll talk about this not necessarily as a 1,2 hydride shift, because those are the number of bonds that are moving, how far away the hydride can jump. It's very rare the hydride can jump anywhere else than one bond away. I will never show you those. So we will just call these hydride shifts. And they're to make a more stable carbocation in an SN1 intermediate. Other group shift, you might have seen it here. This is the only other kind of group that can move is a methyl. Anything bigger than a methyl is just too large to pick up both the piece and the bond and everybody jump over. It just can't happen. So only a methyl. And notice the reason it'll want to do this one is because I'm starting on a secondary carbocation again, and it's sitting not next to a tertiary carbon, but it's next to a quaternary carbon, right? So watch what can happen here. This bond, it will just move over. And now it's made this beautiful, oops, excuse me. Let me come back to this beautiful tertiary carbocation, happy days, and we've done a methyl shift. Okay? So you can only do hydride shifts and methyl shifts, but that's enough chaos. You know they're going to show up somewhere, and they won't show up in SN2 because there's no carbocation. So first of all, you just have to decide, am I doing an SN1 reaction? So what kind of substrates? Let's just overview here. This is the opposite of what is best for a SN2 reaction. I need the bulkier the better. This is ideal. This will never happen. No reaction. I will never be able to make a methyl carbocation. I will never be able to make a primary aliphatic. No reaction. Primary aliphatics can't form carbocations, but primary benzylics and allylics can because they have a possibility of resonance to stabilize the carbocation. So don't hold off on all primaries. So look out for the allylics and the benzylics. Another tricky little thing. Okay? And secondaries can make carbocations. They're middle of the road, and that's always an issue because they're middle of the road. Feel free to come back to this slide, number 10, if you have any more questions about this one. Okay. Oh, just to keep your eye on it, that was a nice, happy, no, not so happy. It looks happy, but really this should be a very sad carbocation, a secondary carbocation. And therefore, it can't wait for that BR to come up and eat it up and actually make a molecule of it. In summary, if I have this reaction, I know this is going to be an SN1 reaction. There are two things that'll tell me. One, and most importantly, this is a tertiary aliphatic. Tertiary aliphatics will never go SN2. So then I look at the nucleophile. Do I have one? Yes. Does it matter that it's charged in gray? Is that going to make it go SN2? No. Substrate can't do SN2, but I have a nucleophile now, strong. Yes, doesn't matter. Could be the protonated form of this. It would still be a good nucleophile. All it needs is a lone pair, and it will react. Okay? So, oops, I wrote over a, that's basically our rate law hiding under there that indicates it only has that one step, slow step process of losing the leaving group. And the nucleophile is not present in the transition state, so that strength doesn't matter. Just going to reiterate that again. And in this reaction, the tert butyl chloride's carbocation is the only compound seen in the transition state. And remember, this is planar. That becomes important for stereochemical reasons if you ever to have a chiral atom there where the leaving group's attached. And the nucleophile will always come in after this slow step, and therefore this creates that hideous racemic mixture if it's chiral. It could also keep an eye out for rearrangements, hydride shifts, methyl shifts, and resonance. These will move this carbocation and then the nucleophile it might add in a completely new place. Tricky, tricky, tricky. I guess that's got to be the case in Orgoland, huh? And last but not least, if you were to pick a solvent to have this carbocation swimming in, would you want it to be nonpolar, aprotic, uncharged? Would that help? No. So here's another last key. If you look at some of the solvents that we decide to use for these SN1 reactions, they are very protic. And that means they have a lot of partial charge. Which is a good thing if you're charged. You can surround that carbocation with a lot of charge and make it feel better. Okay? So again, it's the last thing. Solvent is really the least important out of all of these factors because you could do an SN1 in an aprotic solvent as well. So I wonder what this little blue mole is going to answer here. Maybe in our next Zoom meeting on Monday night, 7 p.m. Don't miss it. All right, you can miss it, but let me know if you miss it. Please get in touch with me before that, and let's hold a separate Zoom meeting. I think we're going to be holding one at, say, 1 p.m. tomorrow, Monday as well. So maybe you can join us for that one. I'll post that on our Sakai site, and I'll also post the 7 p.m. meeting as well, and you can join in any of these meetings to talk about any of these, or most importantly, what the heck is going to happen when I start having to do problems like this one maybe, or how do I talk to Nick about all this through this Orgoland in cyberspace experience. So I hope to get in touch with you in the next day or so, and I'll see you on Tuesday's first class. Keep in touch. Stay safe. See you later, everybody.